or clockwise if m is less than 0. Then that gives us the winding number of that is f tilde f1 minus f tilde of 0, which is equal to m. So essentially this next lemma and corollary here, we're just going to use to simplify the definition of this essentially, because we're going to use this to define our definition of degree. Essentially we want to prove, because we just sort of glibly assumed this, but we want to prove that such an f tilde exists in this next lemma. And moreover, in the corollary, we're proving that there exists such an f tilde with f tilde of 0 equal to 0, so we can simplify our definition. I don't know if that's actually necessary, but it's what they do. I guess it probably makes the later proofs easier. But let's go ahead and do that. Lemma.
Okay, very good. So just to give a rundown of where we're going in the next 2 pages is to prove that the fundamental group of the circle is the
Integers.
The integers.
Yeah. So, sorry, that one got away from me. Let X be a compact convex subset of Rk. So I'm not going to write all that, but then let f from pointed space x at x naught to S1 at the North Pole be continuous. Then let T naught in integers. Oh, and just the definition they use, let x t denote e to the 2 pi it. Then there exists a unique continuous f tilde from x at x naught to r at t naught with what we wanted, x of f tilde equal to f. So in other words, well, they have a diagram there, but I'm not going to draw it because it'll waste time. This is essentially what we want. So proof.
You should drop the diagram, that's fine.
I'm just going to read this because there's a lot of words here, and
you should draw
time.
You could draw the diagram and just talk through the proof.
Draw the diagram, then read it?
Yeah.
Okay, sounds like a good compromise.
What is this theorem? What's this lemma saying?
3.14?
Yeah. Just trying to unwrap it. You have a compact.
Well, essentially, it's the existence of. I mean, it's kind of like the existence of the logarithm of f, but it's from any compact convex subset of some Rk.
Huh.
But what we're going to do in the corollary is restrict that to the case where you have the unit interval. So they kind of prove it for a more general case than we need here. This is what they're doing. But they have an interesting analytic proof here. So essentially this is what we're trying to construct. F tilde. This is our x.
Do you want the composite of f tilde and the exponential to be f?
Right, exactly. So they say since x is compact metric, f must be uniformly continuous. I don't know if we went over that in real analysis, but that sounds reasonable to me. I don't think we did much more than with the real line, so. So they say there is an epsilon, therefore there is an epsilon greater than 0, such that whenever the norm of x minus x prime is less than epsilon, then the norm of f of x minus f of x prime is less than 2. Then they say they choose 2, which is the diameter of S1, to guarantee that these points are not antipodal.
So basically, if your input's less than epsilon units apart, you can force the outputs to be less than the diameter of the sphere apart.
Right, so f of x times f of x prime inverse does not equal -1. So keep that in mind because we're going to use that near the end of the proof. Just keep that in the back of your head.
Yeah.
So now x bounded implies the existence of a positive integer n with the norm of x minus x naught over n less than epsilon for all x element x. So epsilon is fixed. So essentially they're just saying, you know, the norm of the difference between a particular point and any other point in the space is bounded. They're just making this particular choice of n and epsilon, which is a convenient choice we're going to see in the proof in a second. Just to give some context there. So then what they do, for each x element x, subdivide the line segment having endpoints x naught and x, which is contained in x by convexity, into n intervals of equal length using uniquely determined points x naught, x1 through xn, which is equal to x. Then here's where they use the over n. They have the norm of x sub j minus x sub j plus 1 equal to norm of x minus.
Yeah.
Although equal to,
They're equal.
that should be...
No, that's equals. That equals. That's equals because what they're saying is that the length between any particular.
Oh, right, because you're... Oh, yeah, right. Makes sense.
Yeah.
So that is equal to that over n.
And children should be able to understand that step.
Which is less than epsilon. Therefore, here's where the norm of f of x minus f of x prime less than 2 comes in. Therefore, we have f of x sub j inverse f of x sub j plus 1 not equal to -1 for each j in the range that we're considering. So then they define this function for each j, g of j of x, or g sub j of x is equal to f of xj inverse times f of x sub j plus 1. So essentially what they're doing here, they use this telescoping thing here, making use of the fact that S1 is a topological group, which I thought was interesting. So essentially they note f of x, which is equal to f of xn,
Oh, pretty.
is equal to f of x naught times f of x naught inverse f of x1 f of x1 inverse f of x2 etc. all the way out to f of x sub n minus 1 inverse f of xn. So you can see these two are equal. And that is just equal to, by our definition, f of x naught times g naught of x, g1 of x, all the way out to g sub n minus 1 of x. So they say the restriction of x to -1/2 to 1/2 is a homeomorphism from -1/2 to 1/2 to S1 without the south pole. And again, why they can say that is because they have, well, I guess that's because of the original epsilon restriction they had at the beginning, why it doesn't include the south pole, I guess. But anyway, essentially what they do once they have this, maybe you guys have already see it, but they define the f tilde of x to be t naught plus lambda. Oh, did we define lambda?
Lambda's the
Oh, okay,
inverse
so
of
lambda is the
X.
inverse of that
X.
homeomorphism.
Yeah.
So lambda,
So has this given you
fact,
any
is
new
equal
ideas
to-
about finding logs over algebras, Nathan?
1 over... I haven't thought about that yet.
Okay.
1 over 2 pi I.
This is some sort of grand glorious
Times
pseudo
log.
log construction.
So, so this is T naught, is lambda,
Goodness gracious.
G naught of X, all the way up to lambda of G sub n minus 1 of X.
Right.
So when you take X of this, X of F tilde of X, you're just going to get, by the homomorphism property of exponentials, X of T naught times,
X above
these
lambda.
are inverse,
Yeah.
so just G naught of X, G1 of X, all the way out to Gn minus 1 of X. And so, that then, I guess this is equal to f of x naught.
Yeah.
So by this remark up here with the telescoping identity, we have x of f tilde equal to f. So then finally, just prove uniqueness of the exponential. So essentially, they assume that there's another g tilde such that x of g tilde is equal to f. They do some algebraic manipulations to get to x of f tilde x over x of g tilde x equal to 1. And
Yeah.
then they use the fact that x is a homomorphism with kernel z, which I guess forces those to be 0.
Yeah.
But we don't have time to get into much of the details, so
Yeah,
I'm just
fine.
going to move on. Let's see, what do I have to do? I don't think I have enough
So let's just-
time to go to this next corollary.
Yeah, we can just talk about it.
Yeah, but so, like I was saying, the result here, there
have to
exists
write- you don't
unique
have to write
continuous f tilde with x of f tilde equal to f, and f tilde of 0 equal to 0.
So in the corollary, they just put your affine, your compact convex adaptation.
Right, they're just replacing it with I.
In an interval, yeah.
But they also have the second part, if G is continuous and f homotopic to G rel I, then f tilde is homotopic to G tilde rel I.
Right.
That's also important. So finally, we have definition. They define, if f is a path, then we define degree of f to be f tilde of 1. So where f tilde is the unique lifting from the corollary with f tilde of 0 equal to 0. From the preliminary work we did, this is essentially the winding number.
Right.
We just made a choice so that we only have to plug in f tilde of 1. So we have theorem 3.16. Function d given by f maps to degree of f is an isomorphism. So in other words, essentially the degree of f star g is equal to degree of f plus degree of g. Let's see. Trying to see whether or not I want to prove this. Alright, essentially what they do, they look at the kernel of this degree map, and they're trying to show that the kernel is trivial to show that it's injective. And then after that, they have some technical argument where they show that it's a homomorphism. And, okay, so they use this function here, f of z equal to z to m, to show that it's surjective, right? Because if you look at the degree of this function,
Yeah.
it's equal to m, and this is well defined for all integers. So I don't think I'm going to get to the details of that argument, but we have that theorem. From that we have this corollary. This corollary 3.17, which is that S1 is not simply connected. And so, of course, what the last theorem showed us here. Okay, so we have this homomorphism property, but moreover, that this map D from the fundamental group of S1 to the integers is an isomorphism. So in other words, fundamental group of S1 is Z. So that's not a trivial group.
Right.
Therefore, S1 by definition is not simply connected. So now, finally, what we've all been waiting for. Oh yeah, I just noticed you with the light there. Is it still glaring on the whiteboard, or?
I think it's okay.
Okay. So theorem
So
3.19.
delocalized glare.
This is the fundamental
I tried writing it right
theorem
up
of
under the light.
algebra.
You can still see it.
So this is, of course, continuing.
Wait, didn't
Well,
you-
what? I guess in chapter 0, right? Where we had. You guys remember what theorem it was?
I know what you're talking about. I think that's
Yeah.
chapter 1. Oh, 1.5. You're 1.5.
Theorem 1.5.
It's 17.
Yeah, let C denote the complex numbers. Let sigma sub rho denote the circle, the center at origin, 0, and radius rho. If none of these maps are null homotopic, then the fundamental theorem of algebra is true. So now,
Now we should.
about 40 pages later, we're finally going to prove that. So, proof.
You know, Nathan, I'm going to stop you right there. And so next time I'll give you 20 minutes, let's say.
Okay.
And you can do the fundamental theorem of algebra, and also I'm guessing that you want to show that if G is a topological group, then the fundamental group is abelian. Because the proof of that, which is basically it's a corollary to theorem 3.20,
Right.
that looks like it's a pretty mechanical proof at this point. You're actually getting to use all of these things that you've spent so long to build up.
Yeah.
You should spend a little bit more time at this level of...
If you want, then,
Would 20
should
minutes,
I go over?
Would 20 minutes be enough for that, for those two?
Yeah, I think so.
Okay.
Do you think maybe I should go over the corollary 3.15 too, or?
You got 20 minutes, so it's up to you.
All right, I guess it depends.
And then I think by Thursday I'm hopeful that by Thursday I'll be able to talk to you guys for 50 minutes, let's say. That seems plausible.
What is the next? Oh, the next chapter is on singular homology, right? Fun stuff.
Yeah, so we'll get started on the singular homology Thursday. Yep. Well, thanks, guys.